At 4:40 in the afternoon, the Mustang lifted off from Vicenza. The transit was still routine at departure. The crisis would develop later after the aircraft had crossed Valpolicella and was closing on the Lake Garda area, with the impact reported at about 4:55. The aircraft was powered by a freshly overhauled Merlin engine, the Packard-built version of the Rolls-Royce design used in the F-51D. Without warning, this power plant began exhibiting severe and erratic fluctuations in revolutions per minute. The 29-year-old pilot faced an immediate mechanical anomaly over highly restrictive terrain. The initial response was an attempt to resolve the engine trouble in flight, not an immediate emergency landing. Witnesses later described the Merlin's revolutions rising and falling, and the available accounts indicate that Lieutenant Paolo Tito tried to stabilize the problem while maintaining control. But the fault continued to worsen. Whatever checks he could make in the cockpit, the aircraft was losing usable power faster than the situation could be recovered. The worsening engine problem forced a critical aerodynamic threshold. Without reliable thrust, a heavy fighter aircraft can only trade altitude for distance. As the Mustang descended, every second narrowed the terrain it could still reach. Contemporary accounts state that the primary diversion airfield at Gadi became unreachable. Whatever margin had existed was gone. The pilot was now committed to an immediate forced landing. The terrain surrounding the flight path offered very few practical margins for a controlled touchdown. Around the southern end of Lake Garda, the remaining choices included populated ground, obstructed terrain, and the open water itself. Dropping an unpowered fighter into the wrong area could have meant destroying the aircraft in a violent ground impact and endangering people below. The loss of altitude also made bailout a doubtful option. Contemporary accounts state that Tito had lost too much height by this point, and later interpretation allowed that he may have considered leaving the aircraft but misjudged the remaining altitude over the reflective surface of the lake. Bound tightly by these spatial and mechanical limits, the pilot evaluated the remaining terrain within the rapidly shrinking glide cone. The only obstacle-free area wide enough to accept the shallow approach profile of the F-51D was the open surface of Lake Garda. He adjusted his flight controls to target the freshwater expanse, accepting a water ditching as the only viable engineering solution remaining to prevent a terrain collision. The aircraft impacted the surface. Following the event, the military initiated a response. In the days after the crash, the Stato Maggiore dell'Aeronautica commissioned a local firm to recover the pilot's remains and, if possible, the Mustang's guns. Using the diving methods available in 1951, divers descended into the dark water. They recovered the body of the pilot, fulfilling the primary priority of the operation, while the airframe itself remained on the lakebed. The underwater environment dictated strict operational limits. The wreckage rested at roughly 60 to 70 meters below the surface, about 200 to 230 feet. At that depth, any 1951 diving effort imposed difficult time, mobility, and decompression constraints. The available accounts confirm the recovery of the pilot's remains and state that the guns were to be recovered only if possible. They do not confirm a formal decision to lift the entire destroyed aircraft. The practical result was simpler and starker. The bulk of MM4309 remained below. The extraction operation concluded, the diving tender returned to port, and the wreckage was left undisturbed. Over time, the precise location of the Mustang became difficult to recover from ordinary records and local memory. The aircraft shifted from an active mishap site to a submerged historical problem, known through the accident file, eyewitness accounts, and the memory of those connected to the original recovery. Decades passed with the airframe in cold freshwater. The question left behind was narrower and more forensic. Why did an attempted water landing become a catastrophic breakup? During the 1951 recovery, divers found that the pilot's seatbelt had been unbuckled and the canopy unlocked. That evidence suggested preparation to escape, but it did not prove the exact timing or sequence of Tito's final decisions. It supports an active attempt to survive, not pilot error, and it cannot confirm a fully controlled egress strategy right down to the surface. However, the physical interaction between a fast fighter and the water surface overpowered any survival logic. At that speed, water did not behave like a forgiving runway. Contemporary accounts describe the Mustang striking violently, skipping off the lake surface and breaking apart. The F-51D's ventral radiator scoop may have worsened the hydrodynamic loads under the fuselage, but the available reports do not isolate it as the proven cause. What is certain is that the impact imposed bending moments and shear stresses far beyond the ultimate design limits of the aluminum structure. The fuselage sheared, the wings separated from the center section under massive bending forces. The forward firewall failed, allowing the heavy engine assembly to break completely free from its mounts. Without the primary harness securing the pilot to the seat, the blunt force trauma during the breakup sequence proved fatal. Following the destruction of the airframe, gravity and fluid dynamics dictated the descent of the debris. Instead of an intact airplane, a scattered field of torn metal began sinking through the water column. The heaviest, most dense elements like the engine block sank the fastest, hitting the lakebed first. The larger surface area components, such as the separated port and starboard wings, fluttered down at a slower rate, drifting with any subsurface currents before coming to rest in the mud. The torn fuselage sections, twisted propeller assembly, and tail group settled across the impact zone. The tearing action during the crash sequence permanently altered the physical nature of the artifact. The original structural hardpoints engineered to handle lifting loads for maintenance were destroyed or isolated. The structural load path of the airplane no longer existed. Down on the lakebed, the wreckage was fully distributed. Later reports described 6 principal sections with roughly another 20 smaller pieces spread around the site rather than a single intact aircraft. The cold, freshwater environment helped preserve recognizable features, including painted markings and large structural forms, but the metal was still an aged wreck. After decades in the lake, its thin aluminum skin, broken spars, and exposed steel parts had to be treated as fragile rather than load-bearing. The shattered wreckage lay untouched in the cold freshwater for decades. 62 years separated the loss of the airframe from its rediscovery. By 2013, the exact coordinates of the site were completely absent from official military records. Finding the specific wreckage in a vast body of water presented a massive operational constraint. Lake Garda covers an enormous geographic area. A completely blind search of the lakebed using only acoustic instruments would require months of continuous scanning, mapping thousands of empty sectors. To make the search viable, the investigation team required a rigidly bounded search box. The volunteer search organization solved this spatial problem through a practical historical reconstruction. The team drew on Italian Air Force records, local eyewitness material, and the testimony of Egidio Isotta of Lazis, whose father's company had supported the original recovery work in 1951. That testimony gave the volunteers a usable starting point near the old recovery area, turning an otherwise vast lakebed search into a focused investigation. With the operational area constrained, the team used sonar to search the lakebed. The instruments located hard anomalies against the natural bottom, giving the volunteers targets worth inspecting rather than miles of empty sediment. The search had moved from historical reconstruction into underwater verification. However, a sonar anomaly only indicates the presence of a hard target. It cannot confirm the specific identity of a historical aircraft. The lake environment contains numerous sunken vessels, discarded machinery, and generic debris, so the operational requirement shifted from acoustic localization to visual confirmation by camera, where distinct painted features like a national roundel could identify the target. The team deployed a remotely operated vehicle to descend through the water column. Operating the remotely operated vehicle required precise surface handling. The surface crew had to maintain the boat position directly over the target area while carefully managing the long umbilical tether. Any sudden drift by the surface vessel could drag the vehicle off course or entangle the tether in the jagged debris. With no natural sunlight reaching the lake bottom, the vehicle relied entirely on its onboard artificial illumination to sweep the sediment. The live camera feed eventually captured the outline of a large, flat, manufactured structure resting in the mud. The operator brought the remotely operated vehicle closer to inspect the aluminum surface. It was a detached wing of the fighter. As the lights moved across the degraded metal skin, they illuminated a distinct circular marking, the Italian Air Force roundel. That marking became the key visual confirmation, tying the wreckage to the historical records, the location, and the known loss of MM4309. The team had located Tito's F-51 Mustang. The visual confirmation locked the identity of the site, but it also verified the severe physical degradation of the aluminum. The wing lay isolated from the main fuselage structure. Finding the Mustang was only the initial hurdle. Bringing decades-old wreckage to the surface required an ROV-assisted recovery in which the underwater robot helped attach lines and airbags to the main sections, while the Garda volunteers, divers, and support crews controlled the operation from the surface. Each section had to be treated as a separate, fragile load, and every attachment had to avoid crushing or tearing metal already damaged by the impact and decades underwater. This localized approach was required because the physical state of the wreckage dictated a multi-point section extraction. Multi-decade freshwater immersion weakens the structure, the aluminum skin corrodes, and the original aircraft load paths are completely destroyed. Multi-point section extraction acknowledges this degradation by floating the sections independently rather than pulling them from a single surface point. If a standard salvage operation attached a single heavy crane cable to a centralized point and hoisted the load, the unsupported weight of the waterlogged metal and heavy mud would cause the airframe to tear itself apart during the ascent. On December 2, 2016, the physical extraction phase commenced. The team targeted exactly 6 major sections resting on the sediment. Each of the 6 major sections required a bespoke lifting plan. The robotic vehicle approached the first target, carefully thrusting to avoid kicking up a cloud of silt that would instantly blind the live camera feeds. The mechanical arms threaded the heavy rigging. Once the primary strap was secured to a solid spar, a deflated canvas lift bag was locked to the attachment point. The lift then became a controlled buoyancy problem. Airbags raised the sections from the bottom, but the force had to be applied gradually so that a fragile part did not tear free, roll, or surge upward before the surface crew could control it. The goal was not speed. The goal was to separate each section from the lakebed and bring it up without adding new damage. Recovery proceeded section by section. The 6 largest pieces were brought up as separate loads, an approach that kept one broken component from carrying the weight of another. As the individual components broke the surface, the team could finally assess what had survived the violent 1951 impact. The transition from water to air forced an immediate handling decision. As the heavy lift bags broke the surface in 2016, the recovery crew faced the physical reality of the extracted components. The team had to secure and stabilize distinct, torn sections, including the port wing, the massive engine block, and the twisted propeller assembly. This phase demanded a strict shift in operational procedure. The physical state of the wreckage dictated careful surface transport to the nearby shore at Lazis. The localized multi-point section extraction successfully brought the separated pieces up without inducing new stress fractures. However, the items arriving at the surface bore the permanent kinetic signatures of the historic hydrodynamic skip breakup. The aluminum was completely deformed and the pieces were highly vulnerable to the sudden shift in gravity. In the water column, the components were partially supported by buoyancy. In the air, full gravity reasserted its downward pull on the weakened structures. The largest single structure to break the surface was the port wing. It extended from the outer tip inward to the shredded root near the cockpit area. Handling this piece after recovery required caution because a torn aircraft wing is full of voids, ribs, bays, and channels that can trap water and shift weight unpredictably as it leaves the lake. The crew had to treat the wing not as a rigid lifting surface, but as damaged aluminum already weakened by impact and decades underwater. Next, the surface team processed the Merlin engine. Unlike the hollow, high-surface area aluminum wing, the engine was a dense, concentrated mass of steel and alloy. It had separated from the forward structure during the crash sequence, and once recovered it had to be stabilized as a heavy, uneven load rather than as part of a complete aircraft. The twisted propeller hub presented a different handling problem. The crash forces had bent the blades backward into a distorted shape, making the assembly awkward to secure and move. Its uneven geometry demanded careful support during the transfer from recovery equipment to transport. Once all 6 major components were secured on the floating platform, the operation pivoted from deep water extraction to surface transport logistics. The transport vessel navigated toward the harbor at Lazis. Moving these heavy, jagged components from a dynamic floating barge onto stable transport trucks introduced a final mechanical hazard. The transfer required a shore-based hoisting system. The lifting slings had to be carefully routed around the exact same reinforced points verified by the remote vehicle underwater. Placing a strap on an unsupported span of the thin wing skin would instantly crush the metal they had just spent extensive operational time saving. Once the wreckage was out of the lake, preservation became the next problem. The recovered parts underwent washing to slow the oxidation process before transport onward. The transport trucks were loaded and secured, successfully concluding the physical salvage operation. The retrieved metal represented more than just salvaged parts. It was a uniquely rare historical asset. Only one complete Italian Air Force Mustang is commonly cited as surviving. The example at the Italian Air Force Museum at Vigna di Valle. That rarity defines the historical value of the F-51 platform within Italian aviation history. When the flatbed transport trucks departed the shoreline of Lake Garda, they carried the shattered remains of another airframe toward Volandia Park and Museum of Flight near Malpensa Airport. There, the question became not how to make the wreck look new, but how to preserve what had actually survived. A complete restoration would have faced an obvious obstacle. The recovered material was not a complete aircraft, but a violent crash field brought up in pieces. The port wing, engine, propeller, and other sections carried the evidence of the impact itself. Rebuilding the fighter into a pristine shape would have required extensive new fabrication, and the available public reports do not document such a plan. The safer historical framing is to treat the remains as wreckage with evidentiary value. The bends, tears, and fractures are not merely damage. They are the physical record of what happened when MM4309 struck Lake Garda. Executing any preservation strategy began with stabilization. Public reporting confirms that the parts were washed to slow oxidation after recovery, while later listings identify MM4309 among Volandia's aircraft holdings. Beyond that, the exact conservation chemistry, internal engine treatment, and mount design are not documented in the available public sources. What can be said safely is that the wreck could not be treated like a normal, intact airframe. The original load paths were gone, the components were separated, and every display decision had to respect the fact that these sections were fragile crash remains. Positioned as an unrestored wreck, the Mustang does not resemble the pristine fighters usually seen in aviation galleries. Its value lies in that difference: raw, torn aluminum preserved as a record of the final flight, the failed escape from the lake surface, and the difficult recovery that brought the evidence back into view.